Hello, everyone, and welcome. Today we're exploring an exciting journey from agricultural waste to clean energy. Bioethanol production from rice straw pulp. This project is about turning what's often discarded into something powerful, sustainable, and aligned with global goals for a cleaner future. It's a story of innovation, collaboration, and impact. So let's dive in and discover more about this topic together. Let's begin with the bigger picture. Our dependency on fossil fuels continues to drive greenhouse gas emissions. In fact, transportation, electricity, and industry together account for nearly 80% of emissions in the United States. This reliance on coal, oil, and gas is a direct contributor to global warming. But there is a way forward. By turning the dial toward renewable energy sources, we can unlock cleaner alternatives. Among them, bioethanol stands out. Produced from renewable carbon sources like biomass and even carbon dioxide through microbial fermentation. It offers a sustainable fuel option that reduces emissions compared to fossil fuels. Now, let's bring this closer to home. In Malaysia, rice straw is often treated as waste. Farmers burn it after harvest, releasing dust, crystalline silica, and hazardous contaminants into the air. This practice not only pollutes the environment, but also contributes to respiratory diseases in nearby communities. And here's where the opportunity lies. Instead of burning rice straw, we can transform it into bioethanol, turning waste into energy. This approach directly supports the United Nations Sustainable Development Goals, Goal 7, Affordable and Clean Energy, Goal 12, Responsible Consumption and Production, and Goal 13, Climate Action. So, the background of this study is clear. Fossil fuel dependency drives emissions, rice straw burning worsens pollution, but bioethanol offers a renewable solution that aligns with global sustainability targets. Our world today is powered overwhelmingly by fossil fuels. In fact, oil, coal, and natural gas together make up nearly 87% of global energy demand. This heavy reliance comes at a cost: rising greenhouse gas emissions, worsening air pollution, and an accelerating climate crisis. Look at what happens when rice straw is burned in fields. Carbon dioxide, methane, nitrous oxide, and toxic particulates are released straight into the atmosphere. Add to that the daily traffic pollution in our cities, and the result is clear. Our planet is heating up, and the flames of global warming are no longer just symbolic. The problem is urgent. Energy demand is rising, fossil fuel dominance continues, and pollution from agriculture and transport is fueling the climate crisis. If we don't act, the consequences will be devastating. This is where bioethanol from rice straw pulp enters the picture, a sustainable solution to turn waste into clean energy. So, how do we solve the challenges we've just seen? The answer begins with rice straw pulp. Instead of burning it as waste, we can process it into a fibrous pulp that becomes the foundation for bioethanol production. Next comes the key player, Clyveromyces marxianus, a remarkable yeast. This microorganism thrives at higher temperatures, can utilize a wide range of sugars, and delivers superior fermentation efficiency. Together, rice straw pulp and this yeast form a powerful combination. Through bioethanol fermentation, the pulp is converted into ethanol, a renewable fuel that can replace fossil-based energy. And the outcome is clear: a sustainable, plant-derived fuel, symbolized here by the green ethanol pump. Now, why choose this substrate and yeast? Rice straw pulp is abundant, renewable, and cost-effective. It's an underutilized agricultural waste with high cellulose content, making it an ideal feedstock. On the other hand, Cliveromyces marxianus is not just efficient, it's industrially robust, capable of handling diverse sugars and operating under thermotolerant conditions. Together, they represent a practical, scalable solution, turning agricultural waste into clean energy while leveraging a yeast strain perfectly suited for industrial bioethanol production. This is where science meets sustainability and where innovation transforms waste into opportunity. The production of bioethanol from rice straw follows a well-defined sequence of steps. First, pre-treatment is applied to the biomass. This stage is critical as it disrupts the rigid lignocellulosic structure through physical, thermal, chemical, or biological methods, making cellulose and hemicellulose more accessible. Following pretreatment, the process moves to hydrolysis, where complex polymers are enzymatically or chemically broken down into fermentable sugars, such as glucose and xylose. These sugars then undergo fermentation, facilitated by specialized yeast strains, converting them into ethanol under controlled conditions. Finally, the product obtained is bioethanol, C2H5OH, a renewable fuel that can be blended with conventional gasoline, offering a cleaner alternative to fossil energy. Our research methodology is structured into three main stages: sample preparation, hydrolysis, and fermentation. Each step is carefully designed to transform rice straw pulp into bioethanol in a systematic and controlled manner. The methodology begins with sample preparation. Rice straw pulp was dried overnight at 60 degrees Celsius, ground, and sieved to a uniform particle size of approximately 250 micrometers. This ensures consistency and maximizes the efficiency of subsequent hydrolysis. The second stage is acid hydrolysis. 10% weight-to-volume rice straw pulp was treated with dilute sulfuric acid, autoclaved at 121 degrees Celsius for 15 minutes, then centrifuged and filtered. This process breaks down the lignocellulosic structure, releasing fermentable sugars such as glucose and xylose. Finally, we move to batch fermentation. Here, the yeast Cliveromyces marxianus was first cultured aseptically and incubated for 1 day to establish active growth. Only then was the inoculum transferred into the hydrolyte substrate. Under controlled conditions, the yeast converted the available sugars into ethanol, completing the transformation of rice straw pulp into bioethanol. Our analysis revealed that untreated rice straw pulp produced only 15.71 grams per liter of fermentable sugars. However, pre-treatment significantly improved yields. The highest concentration was achieved using 1% sulfuric acid, producing 82 grams per liter of sugar, with a yield of 41 grams per gram. Structural studies confirmed these results. FTIR analysis showed clear changes in functional groups after pre-treatment, indicating successful breakdown of lignocellulose. Meanwhile, SEM imaging revealed that treated fibers had a disrupted porous surface compared to the smooth structure of untreated pulp, evidence of enhanced accessibility for hydrolysis. In summary, the findings demonstrate that optimized acid pre-treatment not only maximizes sugar release, but also alters the fiber morphology, directly supporting efficient bioethanol production. Our invention builds on three pillars. First, acid pre-treatment effectively breaks down the lignocellulosic structure of rice straw, increasing cellulose accessibility and boosting sugar yield. Second, efficient fermentation ensures maximum ethanol conversion. Among the tested organisms, Clyveromyces marxianus consistently outperformed Saccharomyces cerevisiae and Candida bodini, producing higher ethanol yields even at elevated sugar concentrations. Third, process integration combines pre-treatment, fermentation, and distillation in a streamlined system. This reduces energy and cooling costs while improving overall efficiency. The advantages are clear. Rice straw provides a low-cost feedstock, pollution is reduced, ethanol yield is higher, fermentation is faster and more robust, and the final product is a renewable, eco-friendly fuel that lessens dependence on fossil energy. This study introduces several novel contributions. First, it represents one of the most systematic investigations in Malaysia on converting treated rice straw pulp into bioethanol, linking agricultural waste valorization with renewable energy production. It even connects to biodegradable packaging industries, creating a circular economy approach. Second, the use of Clyveromyces marxianus is a key innovation. As a thermotolerant yeast, it can ferment both hexose and pentose sugars at elevated temperatures up to 50 degrees Celsius. This reduces cooling costs and improves efficiency compared to conventional Saccharomyces cerevisiae. Third, the process achieves superior hydrolysis efficiency. Concentrated acid pre-treatment breaks down cellulose and hemicellulose more completely, liberating higher concentrations of fermentable sugars, glucose, xylose, and arabinose, than dilute acid or physical methods. Together, these innovations demonstrate a unique integration of waste management, microbial biotechnology, and process optimization, positioning rice straw bioethanol as both scientifically advanced and industrially relevant. This research has not only advanced science, but also achieved real recognition. We secured an industrial grant and collaboration with Free the Seed, produced a full thesis, and even filed for copyright protection. Our work is under review in an international journal showing its academic impact. Beyond publications, the project has earned multiple awards, from gold medals at iNVEX and iFuture to silver medals at MTE and iTex. Together, these accomplishments highlight both the scientific value and the innovation behind turning rice straw into bioethanol. Thank you for your attention. Let's keep pushing for cleaner, smarter energy solutions. Together, we can fuel a better future. See you next time.